Well, guys, good morning. Rather than have you just watch the screencast of me teaching this last year, what I actually decided to do was teach to an empty room. So right now I'm in my classroom with the lights turned off, teaching nobody. It's kind of poetic. Anyway, so guys, what we're going to do is we are going to pick up where we left off last time, and we're going to dig into the tail end of our conversation about entropy. So guys, in order to do this, you're going to want to grab your equation sheets, and then in addition to that, grab your class notes, and we are going to pick up where we left off, and we will jump in from there, and then we'll move on. So guys, by way of a quick review, if you remember last time in class, minus the video, last time in class we got to the point where we understood that systems or reactions that give away energy tend to happen on their own. They tend to be spontaneous. And we talked about some examples of what those things might be. And then we came to the idea of this quick cold pack. And we were stumped for a minute because we realized that this quick cold pack is spontaneous. We didn't have to do anything to the quick cold pack in order to get it to be cold. So it was spontaneous, but it was not radiating energy. It was actually absorbing energy. And as we got more into that idea, we talked about the idea that it was actually still releasing energy. But strangely, it was the energy of disorder. And as we talked about that idea of the energy of disorder, we looked at our gas cylinder model, if you will. And as we looked at this, we talked about the idea that if we remove the barrier between these two gas cylinders, that this gas is going to evenly spread out between the two cylinders. And guys, that happens spontaneously. We don't have to heat it. We don't have to squeeze it. That happens all on its own. But then we also talked about the idea that while this is spontaneous, it does not give off heat. As a matter of fact, the temperature doesn't change. And so we asked the interesting question, why is it that this is happening on its own? Why is it spontaneous? Why, maybe a word we should talk about, it's not reversible. Guys, this reaction, this process has a direction it goes, spreading out. It has a process that it doesn't go, recollecting in either cylinder. So this is irreversible and therefore spontaneous. And we talked about why. What is it that is driving this process to happen all on its own if it's not a release of energy, of heat, of enthalpy? And we got to the idea that the answer is something called entropy. And guys, this is where we're going to pick up today. So what is entropy? And guys, entropy is defined as, and I know that the video talked about the idea of energy spreading out. And that is a wonderful way to think about it. But guys, for our purposes, we're going to be just fine thinking about this as the disorder of a system. Now guys, you'll notice that in this definition, it says disorder and not order. And that's important. It's important that we understand this as disorder and not as order, because that will change the sign of the change. So if we think of this as disorder, and if something's becoming more scrambled, that would be an increase in entropy, an increase in disorder. Now understand, if the opposite were the case, and if we think of entropy as order, then if something gets more scrambled, we would say the entropy change is negative because order's going down. So guys, it's really critical once we get into the math of this that we understand that entropy is disorder. And guys, as you might assume or guess or maybe expect, The abbreviation makes absolutely no sense. The abbreviation for entropy or disorder is S. Don't ask, don't know, just deal with it. But guys, the take-home message then, or the tying thought, is that the more disordered or random a system is, the larger its entropy. Now guys, this is where this gets to be a little more, I guess, interesting, because when we start to look for entropy, it's not enough to just keep our eyes focused on one part of an interaction. As we track heat, we talk about heat leaving a system to the surroundings or coming from the surroundings into the system. But guys, when we talk about entropy, we need to broaden our focus. And so the way to do that, the best way to do that, would be, oh shoot, I just forgot her name. Our video friend, her. I'm sure you remember her name. But guys, this is now probably the fourth time we've watched this video. Actually, I'm going to cut the sound out of it. But let's let this go. And guys, I'm going to play it through once, and that, well, not all the way. I'm going to play a portion of it once. But guys, what I want you to do is I want you to watch this video through the lens of disorder. So guys, be looking for high and low levels of disorder. So again, salt dissolving in water. There's our salt. That is what we call a crystal lattice. We'll talk more about that later. As you know, in come the water molecules. And guys, the water molecules surround, remember intermolecular forces, the water molecules surround the ions in the salt, and like little tugboats, it carries these ions off into solution. Now guys, stopping the video right here, stopping the video right there, and actually I wanted to move it back just a little bit. So guys, let's talk about the entropy of this crystal. So I'm going to give you a second to chat with the person next to you. So guys, is the entropy of this crystal relatively high or relatively low? Chat about it. So guys, now that you've had the opportunity to sort of identify whether you believe that it is high or low, let's talk about it. And so guys, crystals, by definition, have very, very low entropies. They are very ordered. You can see the structure. You can see the repeated pattern. You can see that things are locked into place. And so guys, as a result, crystals are understood to have very, very low entropies, low disorder. So then continuing on, you know where the video is headed. In comes the water molecules. And guys, keep an eye on what happens to the ions in the salt crystal. So guys, as the video plays, you can see that the water molecules are carrying these ions off into solution. And the question then becomes, what is happening to the entropy of the NAs and the CLs as they dissolve in water? Again, guys, take a second and talk about it. Is the entropy of the salt going up or is it going down? So guys, I suspect that that was a fairly easy question to address, and you see that the entropy of the salt is going up. But guys, the interesting thing here, and I'm going to back up just a little bit, is taking our focus off of the salt. So we've identified that the salt lattice starts at low entropy, and as it dissolves, it goes to an increasing state of entropy. But now, guys, what I'd like you to do is I'd like to turn your attention to the water. And if you're looking at the water molecules, maybe, for example, you turn your attention up here to the upper left, Guys, talk to the person next to you about the entropy of those water molecules, especially if we were to put this in motion and allow it to play. Is the entropy of the water high or low, relatively? And guys, as you're answering this question, maybe it would be helpful to remind yourself of the description last year that we used of liquids. Guys, remember that we said that liquids are like mosh pits, moving at hundreds of miles an hour, slamming into each other, craziness. So guys, giving you a moment to sort of think through that. I think that probably we would agree that the entropy of the water is higher. Higher certainly than the crystal. But guys, these liquids have higher entropies. They have more freedom. They're more mucked around. They're more disordered. And guys, you're going to find out later in the morning that that is almost always the case. We'll say always the case. That liquids have higher entropies than solids, and then gases have higher entropies than liquids. But guys, now let's let this continue to play. And let's see what happens. I was afraid of that. As this continues then to play, wait for it. As this continues to play, let's go here and let's allow this to continue. And guys, you can see what's happening. The water molecules are carrying the salt off. Now, guys, this is an interesting place to look. What happened to the entropy of the water as the salt was dissolving? Take a second and chat about it. So guys, looking at the image that's up on the screen, I'm hoping that you can see that the water is now currently in a more, I almost said more organized, bad. The water is actually in a less disorganized state than it was when it was just floating around free in the liquid. And so guys, the entropy change for the water is actually negative. The entropy of the water is going down, and the entropy of the salt is going up. And guys, this is an important thing, that when we think about entropy, we don't any longer get to just look at our system. We also need to take into consideration everything that's going on around it. And so guys, with that as a backdrop, and you don't really need to write this down. Sorry, my screen is struggling. Still struggling. Okay, this is going to freak out for a minute. Oh, it didn't. Hey, look at that. So guys, when we consider a process like this, and I think that you can just agree with this rather than writing it down. When we consider a process, not the following, the previous process, dissolving salt in water, guys, this is an endothermic process. Think through this with me. So this actually takes in heat. We'll tie it to entropy in a minute. But the dissolving of table salt in water is actually endothermic. Now guys, if this process is endothermic, should it be spontaneous? Because I'm going to pause for a second and chat about that. It's endothermic. It takes in heat. It would feel cold. Should that be spontaneous? So guys, can we come together and agree that this process based on enthalpy change should not be spontaneous? Remember, we established at the beginning of last time's class that things that are spontaneous tend to give away heat energy. And this does not. It's actually a very similar process that's going on inside our quick cold packs. And so it's not as extreme as ammonium nitrate dissolving in water, but it does feel cold. And so this should not be spontaneous. But guys, is it spontaneous? Is dissolving salt in water spontaneous? And obviously the answer is yes, because salt dissolves in water. So guys, now the question is why? Why would dissolving salt in water be spontaneous if it takes in heat? Guys, take a second and think through that. Why would this be spontaneous? Let me ask it differently. What makes this spontaneous if it's taking in heat? I'm going to give you a little more time. Talk about it. Why is this spontaneous if it takes in heat? So guys, wrapping up your conversations, let's talk about it. So what is going on? Dissolving table salt in water takes in heat, enthalpy, and yet it's spontaneous. And how can that be? And guys, the interesting answer to that question is that while this reaction, well, this process, it's not a chemical reaction, while this dissolving process does take in heat, there is an offsetting increase in entropy that is releasing more energy in the form of disorder than the process is taking in the form of heat. And so guys, if that was a little vague, maybe we draw a little bit of a picture. So the idea is this. This is our salt, and the salt is dissolving into the water. Oh, let's draw a beaker. So the salt is dissolving into the water. And as the salt dissolves in the water, it is taking in energy, the delta H, the enthalpy change, from both the water and then also from the surroundings. That enthalpy change is positive. This is endothermic. It's taking in heat. But guys, what's happening is as the ions in the salt spread out into the water, this is releasing more joules of energy in the form of disorder as are going in joules of energy in the form of heat. And so guys, that is then the driving force behind this process. As the salt spreads out in the water, the amount of energy in joules that is being given off in the form of disorder is greater than the amount of energy that's being taken in the form of heat. And guys, I know that that's strange to think about disorder as being an energy. But guys, that is very, very much the case. We can measure disorder in joules, in energy units. And so guys, in this particular case, the salt dissolves in the water because the amount of energy being lost in the form of disorder is greater than the amount of energy that's being absorbed in the form of heat. Okay, so guys, this then brings us to three important questions, well, thoughts as we get into this. Guys, when we are considering entropy, when we are considering disorder, we need to consider more than just one particular part of a system. What we need to do is we need to identify all of the ordering and disordering processes. And as we do this, the disordering processes are the ones that predominate. And guys, I know I hedged a little bit there with the idea of usually. There are some strange exceptions. But guys, understand for our purposes, when we think about entropy, we got to look at the whole shooting match. And guys, when we do, we need to find the ordering and the disordering processes. And the disordering processes are the ones that tend to predominate. Okay, so guys, moving forward then, we need to now talk about what is called the second law of thermodynamics. This is the law of thermodynamics that speaks to this idea of disorder. Now, guys, let's review quickly the first law of thermodynamics that says that energy is conserved, that energy in is equal to energy out, and kinetic can interconvert between potential, and there's no energy loss. Unless it's nuclear, but that's a different story. But guys, at the end of the day, the energy in the universe is fixed and it just moves around. And so energy in is equal to energy out, and a kinetic and potential can interconvert, no net loss in energy. Energy is conserved, first law. Second law is different. Guys, unlike enthalpy, when we consider entropy changes, we've got to consider the system and the surroundings. And guys, this then leads us to the second law of thermo, which says this. The total energy, that wasn't quite exactly right, my fault. So guys, the total energy change in a process is then what we call the total energy change of the universe. And guys, we'll get to this, a statement of the second law in a minute. Sorry. We need to sneak up on this. So guys, sorry, let me back up just a second and let's reconnect. So second law of thermo, we'll come to the definition. But guys, when we talk about entropy, we've got to talk about not just the system or the surroundings. We've got to look at everything. Where's the ordering? Where's the disordering? We call this the energy change of the universe. Now guys, this is taking into consideration both the system and the surroundings. Now, this is kind of the dumbest equation on the planet. You don't need to write it down. But guys, basically what it's saying is the energy change for the universe is what's happening to the system and what's happening to the surroundings. So, with that in mind, let's tie this to reversibility and then to spontaneity. So guys, it goes like this. If you have a system that is reversible, and guys, remember the tight definition of what that means. It means that it is going in both directions simultaneously. This is at equilibrium. Now guys, not surprisingly, the entropy change for the universe is zero. What is happening is being perfectly undone by the thing that is doing it. And guys, because it is being perfectly undone through the same pathway, the entropy change in the forward direction is offset by the entropy change in the other direction, and there is no net change in entropy. That's a system at equilibrium. Imagine ice freezing and melting at the same time. You've got the same amount of ice, you've got the same amount of liquid water. Their entropies don't change in net. But then what if we have an irreversible process? What if we have a spontaneous process? Well, if we have a spontaneous process, the entropy change for the universe is greater than zero. It's positive. So guys, let that rattle around for a minute. Anything that happens spontaneously, the entropy change of the universe is greater than zero. It's positive. So what does that mean? Well, guys, it means that the disorder of the universe goes up. And maybe you picked up on this in the video, maybe you didn't, but there is no law of conservation of disorder. Actually, it's quite the opposite. The disorder of the universe is always going up. And so for any process that isn't at equilibrium, that process is creating an increase in disorder. And maybe you remember from the video that we watched the idea of an air conditioner, that an air conditioner drops the temperature inside your house. Those air molecules are now moving slower. They're cooler. And as the air molecules in your house slow down, their entropy goes down. And so cool air has less disorder, less entropy than warm air. So we are actually dropping the entropy inside the house. Well, how does that happen? And the answer is go to the power plant where they generated the electricity to cool off your house, and they are taking fossil fuels or whatever that might be, and they're burning it, and they are creating a pantload of disorder as organized things like coal get turned into crazy things like heat and smoke and all of the highly disordered things that come out of that power plant. And what we know is that the decrease in disorder inside your cooler home is less than the increase in disorder that's going on at the power plant. Now, guys, this then leads us to this thought. In any spontaneous process, the decrease in the disorder of the system must increase the disorder of the universe by an equal or greater amount. So, guys, anything that we see happen, you know that somewhere in the universe there is an offsetting increase in disorder that is greater than any decrease in disorder that you might see locally. Okay, so guys, with that as a foundational framework for this idea of entropy, what we're now ready to do is we're ready to start quantifying entropy. And guys, as we do this, we are going to relate it to enthalpy. So guys, we've got this idea of heats of formation. And heats of formation is the amount of energy that's released when a compound is made from its component elements. Well, guys, we can also similarly talk about entropy and the components of reactions. But guys, the conversation is different. See, guys, when we talk about enthalpy, we talk about enthalpy changes, how much heat is released when something gets made. But guys, entropy changes are really difficult to measure and think about. But guys, the thing that's interesting about this is we can actually calculate absolute entropy values for substances. So literally, you can say, okay, I've got a chunk of coal. How much entropy does that coal have? And guys, it's a function of mass, it's a function of crystal structure, it's a function of temperature. But guys, we can actually take an object and go, oh, there's the object. I can tell you how much entropy that object has just sitting there. And so, guys, these are what are called standard molar entropies. So these are abbreviated S naught. The naught, again, means standard conditions. But guys, these are measured in the units joules per mole Kelvin. Now guys, I'm going to take a second and I'm going to write this as a whoa. That is not a very good looking J. So guys, we've got, that's not much better. We're going to have to do it. We've got joules over moles Kelvin. So what does this tell us about the entropy of a substance? Well, the first thing that we know is that the entropy of a substance can be quantified in energy units, joules. But guys, this also tells us two other very important things. First of all, moles. How much stuff? Guys, the more stuff you've got, the more disorder that you've got. 2 moles of something will be twice as disordered as 1 mole of something. So guys, if you've got a kid's bedroom and they have 5 toys, that can get pretty screwed up. But now if they have 10 toys, they can actually screw up their room twice as much because they've got twice as much stuff to screw up. So entropy is a function of amount. But guys, it is also a function of temperature. The hotter the thing is, the more that thing moves around and the more disordered it can be. So guys, with that said, and I think my screen's going to muck up again. Hang on. All right. I've learned my lesson. Just a second. Boop, 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 boop. Guys, this leads us to some important guidelines. Some of these will need to be contrasted with enthalpies. But guys, first of all, this. Unlike the enthalpies of formation for compounds, and you may remember that we said the heat of formation for the diatomics is 0. The heat of formation of elements is 0 because they're just elements. Well, guys, while these elements don't have enthalpies of formation, they do have entropy. An element has a disorder associated with it. So the entropies of elements are not 0. Second of all, and guys, I would underline this like 11 times. The AP authors love to hound this. The entropies of gases are greater than liquids. Can you picture that? Gases are flying around crazy. Liquids are stuck together in a mosh pit. And liquid entropies are greater than solid entropies. Can you picture that? In a solid, they just sit there and vibrate, and in a liquid, they're more free to move around, because this is a critical idea. Number 3, the heavier something is, the more disordered it tends to be. Picture a really, really tight, physically fit person. They're sort of locked in place. But if you get a big old sumo wrestler, there's just stuff going everywhere. Sorry, that was weird. Heavier things are more disordered. Number 4, the more complicated a molecule is, the greater its disorder. So guys, for example, if you have methane, which is CH4, or if you have propane, which is C3H8, the propane at the same temperature would be more disordered because it's got more things and therefore more opportunities to be disordered. And then guys, finally, the longer a molecule is, the more disordered it will be. So for example, if you, oh shoot, my bad. Okay. So for example, if you have a molecule like hexane, and there are hydrogens all around this, or if you have a molecule like cyclohexane, we'll use this in lab later. Exactly the same formula, 6 carbons, a bunch of hydrogens. I didn't draw the hydrogens. But the longer molecule will have a greater entropy than the molecule that's all balled up. Longer things are more wiggly, and they have greater disorders. Okay, so guys, with all of that said, we need to be able to now measure, well, calculate, kind of like Hess's law. But guys, we need to be able to calculate entropy changes for systems. Now guys, as I said, you need to grab your AP equation sheet. You'll find that this is there right with the Hess's law heats of formation thing. But guys, notice the differences. First of all, the ends aren't there on the sheet. But then guys, you'll notice that these are not entropies of formation. It's not delta S sub F. These are not entropies of formations. These are entropies of the substance as it's sitting there. Guys, everything has disorder, and we are quantifying and using in calculations these disorders. So guys, this then leads us to calculations. And guys, it says this: calculate the delta S for the synthesis of ammonia from nitrogen and hydrogen. So guys, getting started, we need an equation. Now guys, we've got to balance it. We need a 2 here, and we need a 3 here. And now this is balanced. Now guys, along the way, let's do this. It's going to be sort of awkward, but let's do it. This is a gas, this is a gas, and this is a gas. Now guys, before we do any math, I would like for you to please make a prediction. What do you think the entropy change for this process is going to be? Will it be positive, negative, or 0? And guys, let's just rule out 0 right now. We know that this is not going to be 0. Oh, well, maybe we should do a question. How do we know this is not going to be 0? And guys, I'm not going to give you time to chat about it. I'm just going to show you. The entropy change is not 0 because this is not equilibrium. So we know that it's not going to be 0. So then the question is it positive or negative? Will the entropy go up or will the entropy go down? Make a prediction. Talk about it. Does the entropy in this process go up or down? Sorry if that sounds weird on the recording. I'm trying to stay hydrated. Does the entropy go up or does the entropy go down? So guys, now that you've had the opportunity to think about it, let me give you the answer. The entropy goes down. The question is why? How would you know that without doing any math? How do you know that the entropy is going down? Talk about that. How do you know the entropy is going down? So guys, wrapping up your conversations, this is a really important question. Guys, don't miss this. The AP authors love to do this. So guys, this is how to think about predicting entropy changes. Guys, the very first thing that you do is you turn your, oh shoot, sorry guys, this is gas, not aqueous. I apologize. That's gas and not aqueous. So the first thing that you do is you turn your attention to the phase. And everything is a gas. So guys, as a result, we don't have a phase change that would indicate a change in entropy. Now guys, it's not, but what if this was an S for solid? Well guys, if this change was taking gases and turning them into solids, that would be a decrease in entropy because gases have greater disorders than solids. But guys, that is not what's going on. And again, my apologies for saying aqueous. Guys, this is also a gas. So we don't have a phase change. So what then is the predictor of the disorder? And guys, the answer is the number of moles. There's 1 mole of this and there's 3 moles of this. That means there are 4 moles of total reactant and there's only 2 moles of product. And guys, more stuff means more disorder. So this will create a decrease in disorder because we have a decrease in number of moles. So now guys, let's do the math and let's prove that this is the case. So this is what it looks like. I'm going to use the equation off of the equation sheet. So guys, delta S is equal to sigma, the entropies of the products, minus sigma the entropies of the reactants. Then guys, I'm going to move further to the left to give me space. So that would be delta S for the reaction is equal to products first. So that would be the quantity 2 times the entropy of NH3 minus the sum of 1 times the entropy of N2 plus 3 times the entropy of H2. So now, guys, we need the values for these numbers. I'm praying that we don't have to go all the way to the very back of the book. So let's hope that it's in chapter 19. So guys, looking in chapter 19, please not the back of the book. I'm scared of the back of the book. Well, maybe we're headed to the back of the book. Interesting. That's interesting. Okay. Well, guys, I guess they don't have an entropy table. Yeah, sorry. I'm sort of wasting our time here. So, guys, they don't have an oh, wait. Standard molar entropies. Here we go. Look on page 815. Is ammonia there? Come on, NH3. Nitrogen. Oh, everything's there. Okay, so guys, we have the information that we need. So looking on page 815 in the right-hand margin. So guys, first of all, we need the entropy of NH3, and it's 192.8 joules per mole Kelvin. 192.8. So this would be 2 times 192.8 joules per mole Kelvin minus the entropy of nitrogen, which is 191.6. So that would be minus 191.6 joules per mole Kelvin plus the entropy of hydrogen, which is 130.7. So 3 times 130.7 joules per mole Kelvin. Now, guys, an important thing to notice here is that these values are in joules and not kilojoules. Enthalpy changes tend to be in kilojoules. Entropy changes tend to be in joules, and that's going to be important when we start doing Gibbs free energy when we get back together. Okay, so I have 2 times 192.8. So, oops. That would be 385.6, and that is then minus 191.6, and 3 times 130.7, add those up, and I get 583.7. Guys, let me check that. All right, so either I made the same mistake twice or I got it right. And then 385.6 minus 583.7, and I get negative 198.1 joules per mole Kelvin. But guys, the important part here is notice that the number is negative. We predicted that the number would be negative because we have 4 moles of gas becoming 2 moles of gas. But again, guys, the math works out, and that's where we end up. Okay, so guys, that is the rest of what we need to talk about with entropy. This then leads us to our homework. And guys, the homework goes like this. It is a little bit involved. You have this because I gave you a copy of the class notes. But guys, give yourself time and space to work on this. We'll get together next time and we will look at Gibbs free energy, and then we'll be looking at a test next time. So guys, have a productive rest of your day, whether that's working on homework or writing up labs. We all have lots to do, and we'll look forward to seeing you next week. Okay, have a good weekend.